Hey, welcome back to the Church House Engineering series, where I'm working on solving a practical mechanical problem of building a ceiling that can cover and uncover over a bedroom within a larger church sanctuary. Where we left off in the last video, I have a set of prioritized requirements and constraints. This critical first step now allows us to objectively evaluate how well a given idea is going to solve the problem. Now, finally, in part 3, we can enter the design phase. Let's get at it. What many people feel at this phase in the process is called the tyranny of the blank page. With the combinations of parts, materials, shapes, dimensions, and mechanisms I could use, there are effectively an infinite number of possible designs out there. But in reality, only a tiny sliver of them could meet the requirements. How on earth do we find the one that works best, or at least one that works well enough? So there are two approaches we could take to this. The first is called point-based design in engineering terminology. In normal people business jargon, we would just call it brainstorming. You sit down with a team and crank out the biggest list of ideas you can think of, then evaluate them one by one. Maybe none of the ideas will work exactly as is, but one of them might be a starting point that could be altered using other ideas to get you closer to that final goal. You keep iterating the tweak and test cycle until eventually you arrive at something that works. Most of the time, this unstructured process is good enough for problems that don't have a lot of uncertainty and are similar to something that's already been solved. This is what I was doing in my brain before I started writing requirements, coming up with a design that was a fully formed picture of a solution, and then trying to think of all the pros and cons of it. Unfortunately, the more I learned about the requirements and the constraints, I started to run into walls. There were simply too many factors to keep in mind at the same time, and I knew I was missing things. So I'm going to try a different approach now, what you might call set-based design. First, break down the problem into components and identify what is the broadest possible set of solutions for each one. Then think of how the components affect each other when they're all integrated, and eliminate any subsets that won't work. As you get further into the project and learn, you begin to narrow down the possibilities without committing to any final decisions that don't need to be made yet. You'll use experiments and testing to gain a more focused picture of a workable solution until you have a design that will most likely meet all the requirements. Now, this all sounds pretty abstract, but I'll show you what this looks like in real life using a tool called a Zwicky morphology box. Step 1. Determine the key components of the design, the big decisions that will need to be made that affect the final form of the solution in some significant way. Now, we don't have to list all the decisions here because not all of them are architecturally significant, and they can be adjusted later. For example, the color of the ceiling will certainly matter for the aesthetics, but it doesn't really affect anything else in the design, so I can defer that decision. For this problem, here are the 4 key components that I've come up with. First, the extension mechanism. In other words, what physical shape will allow the ceiling to transform between open and closed? The force actuator. What will drive the movement of the ceiling from open to closed and back? The supports. How will the ceiling be supported by the walls and kept from falling into the room? And then the materials. What basic type of materials will it be made of? Now let's make a table with the components as the column headers. Step 2. Brainstorm out all of the possible values for each of these parameters. In the table under each column, list out the conceivable possibilities for how that parameter could be implemented. I'll go through an example for my first parameter, that extension mechanism. The designs that I could think of: A. Fold out like an accordion with panels in alternating directions. B. We could roll out rows of solid pieces, kind of like a wooden mat. C. You could have a roof with panels that nest under each other and slide out laterally. So D. We could use louvers that, like a shade, when you pull a cord, and you can rotate the slats simultaneously. There's the basic garage door design that slides from vertical against the walls to horizontal on rails. You could do a simple one-piece hatch that just folds down and up. We could get really creative and make a cover that inflates over the room. And then finally, not to throw out any possibilities, what if we just put a fixed ceiling over it, either opaque or more likely transparent. So I've done the same now for all these parameters, stretching my brain, scouring the internet, and talking to other people to try to get every possible idea I could think of. When I'm done, my table looks like this. I can now take a single permutation of these parameters and describe a single design, like CAGC, which would be described as sliding panels that are pushed open with a telescoping arm, supported by beams that cross over the room, made of a solid material. Or BBBB, a roll of canvas that's pulled out by cables, which then are kept taut once it's opened. If I've done my job, the permutations of all these values across the parameters form the full set of possible solutions, and somewhere in that set lies the ideal solution. With the number of values in my table, that's 8 times 3 times 9 times 4, that's 864 possible general designs. So how on earth do we narrow it down from there? To start doing that, we get to step 3. Eliminate any values that don't meet requirements. Makes sense. Here's where I will start to test, quote unquote, the solutions with a simple mental exercise. Before we start putting any of these values together into designs, it's pretty obvious some of them will not work regardless of the other parameters. For the extension mechanism, we can eliminate 4 of the 8 possibilities. Louvers, even if they're open, they're still going to be a pretty significant hindrance to the upward view, which I don't think will meet the aesthetics requirement. A garage door, that has to be able to slide into somewhere when it's closed. And we don't have a space on the side of the room that this can be done without it moving directly over one wall. So that's not going to work with the physical constraints of furniture and safety. Same thing with a hatch that flips open. There's no room in any direction above the rooms for it to move and fold and get out of the way without basically being a completely vertical thing when it's open. Inflatable cover, that might physically work, but it would probably be pretty fragile, just like every bouncy house at a birthday party, and it would look atrocious, let's be real. So if we keep going with this, we can eliminate 3 of those 9 force providers, 1 of the support types, and 1 of the materials right off the bat. That brings us down to 4 times 2 times 6 times 3, 144 possibilities. Let's keep going. Step 4. Eliminate any permutations that won't work with each other. Though the parameters are supposed to be as independent as possible, some values will simply not work with others, usually due to physical impossibilities. One big way I can reduce possibilities is looking at the fixed ceiling idea with no extension mechanism. That idea will only work if it has a way of being transparent or opaque. In other words, smart glass that can use an electrical current to switch between the 2 modes. It doesn't have a force provider, since it doesn't move, and it will definitely require cross beams through the center of the room because there's no way we can have the entire ceiling be one transparent piece of glass or plexiglass. So I can eliminate all those other combos from the extension mechanism. So once I'm done with all of this, I'm left with 11 general designs that might be feasible to meet requirements. All right, step 5. I'll rank each of these designs against the requirements, and this time give a numeric score for how well each design meets it. Since I've prioritized the requirements, I can compute a weighted total score, which will give sort of a subjective measure for the goodness of each design. Now, the top score doesn't mean that I have to go with that design, but it gives me the best candidates that I should choose next to advance in development. I've also got my wife to give her opinion on these and help me prioritize and weigh these. After the numbers have been run, it looks like the accordion design is the leading option for the extension mechanism, and my wife also likes the look of that one the best. Now I've come up with a general design that I want to pursue, but to get any further, I will need to come up with some more specific designs and run some tests on how feasible they will be. Now, finally, I get to go make a physical prototype. Well, that took a while, and in the process I learned some things about design for manufacturing. But regardless, now I have something to look at. I can push on, pull, see physically how it works out. The basic design involves a series of panels joined together with hinges, forming a zigzag shape. They start in an open position, which should be able to stay up relatively flat and no gaps. Now as I close it, it will fold flat into a pretty small compact box shape against that wall. This was just something that I hacked together using cheap materials and made some arbitrary decisions about it as a demo. This is not going to be how the exact real thing works. It doesn't tell me whether it even meets the requirements. There's a lot of details yet to be answered. How many panels will I have? How wide and thick will they be? Where will the wheels be positioned? How will the shape of the rail look? Will they flatten out one at a time, or will they all come out simultaneously? Lots of design decisions that still need to be made, and I can't really figure all of these out just by doing mental exercises, and I certainly can't figure it out by building a prototype of every single one. This thing took a long time to make, and even this is a really quick and dirty, cheap thing. It's got high friction in the joints. It's not going to tell me whether a motor could open up this particular version. Trying to build prototypes of everything is simply not going to work. Not going to be time or money feasible. So what do I do to figure out the next stage of the design without wasting a bunch of time? I'm going to take advantage of a powerful tool in engineering, simulation. This will allow me to create virtual versions of many design variants, easily adjust the parameters, and simulate the real-world physics of the motion. There are lots of kinds of simulations out there, and 3D modeling tools like Autodesk Fusion 360 can provide detailed models that move, and it even has some dynamic simulation capabilities. But I don't know the software that well, and it'll be a steep learning curve and probably overkill for what I need. Since these ceilings will only be moving back and forth in one direction, all I really need is to model the shapes and the forces and the movement in 2 dimensions. So the technical term for what I'm looking for is a constrained 2D rigid body simulation. I found a library called Box2D that was designed to be a game engine for simple games, but it turns out it has a pretty accurate constraint solver for any kind of 2D physics simulation, and it has graphical animation built in. It has a Python API, so I can create exactly what I want in code, and within a day, I had a basic working simulation where I could start testing my designs. Alright, so here's the first simulation I created that represents the same panel configuration as the physical model. This graphic represents a vertical cross-section of the room with the inner wall on the left side. The panels are starting out closed, and each panel has a wheel at the top, suspending it on this rail that stretches across the top of the wall. So when I start the program, it will simulate a 50-pound force pulling out on the outermost wheel. We can see all the panels opening together in that accordion shape, and then this is what I knew was going to happen. Because nothing is supporting the bottom of the panels, the only thing that's causing them to flatten out is that horizontal force pulling the pair apart. 50 pounds is not enough to flatten them completely, but in fact, I could increase it to 500 pounds and it still wouldn't be completely flat. We can understand why by going back to Physics 101 and looking at a free body diagram of the system. Let's just look at the movement of one pair of panels. They'll start folded vertically, and then are pulled outward by a force on that yellow wheel. Now let's pause and examine all the forces in play. First, there's the force of gravity, equal to the weight of the panel. It will be applied downward from the center of mass of the panel, shown in the green crosshairs in this diagram. Then, because the right side of the panel is supported by that wheel, the normal force is applied in the upward direction at that point. We have the horizontal force of whatever mechanism is causing the movement, and at the other end, at the joint with the previous panel, a tension force pulls it both outward and upward at whatever is the angle of that panel. Now think about how these forces affect rotational movement. When a force is applied to an object that can freely rotate about an axis, that is called torque. If we sum up the torques around any point, we'll choose the wheel for simplicity. If the panel tension, trying to rotate it clockwise, exceeds the gravity force trying to rotate it counterclockwise, it will move clockwise. But as we continue to rotate the panels flatter, because the angle between them is closer to 180, we need more force to generate the same orthogonal force to counter gravity, because gravity is closer now to a right angle, and we will generate a smaller torque. So in order to flatten the panels entirely, we would need practically infinite pulling force on that wheel. The physics says it's not going to work. So I need to come up with some design alternatives to make this feasible. One way to reduce the torque required to rotate the panels is through the principle of cantilever. I can move the wheel, which is the rotation point, closer to the center of the panel, so it's closer to the force of gravity. Because torque is proportional to the distance of the force from the rotation axis, this reduces the magnitude of the torque from gravity on the system, making it easier to rotate. Here's the simulation result when I moved the wheels closer to the middle. It has a much easier time flattening out the ceiling, but it still doesn't quite get to completely flat. I need it to be flat and flush because any gaps where the edges by the wall can't press up against the surface above it will let the sound come straight through. But the only way to get that flat is by adding a new vertical force to the system. I gave some thought to putting in a cabling system, which somehow pulls the panels upward by the same force that's pulling them outward. But that's pretty complicated, and even that couldn't quite get it flat. That final bit of motion, just to close the panels, is just too much force. So I thought of a different way to apply a force, adding a second rail and a set of wheels on the lower section of the panels. As they move outward and contact the rail, it applies a normal force to the lower wheel, so the panel rotates as it rolls up the rail. I call this the train design. This worked pretty well, except that when we get to that last pair of panels, we run into the same problem. The rail can't help out with that one, and we can't apply enough force to pull it flat. But this seemed like it was on the right track, so I kept investigating how I could use more rails to achieve the kind of motion I wanted. This solution got really close. By detaching that last panel and supporting it with its own rail, I'm able to get the ceiling completely flat. The only downside is it leaves a gap at the end that needs to be covered by a length of fixed ceiling above it, and that might look a little weird to have a random inset in the ceiling. So I kept trying. Finally, I arrived at something that I think will work. We put the lower wheel of the last panel on a vertical rail so it can slide upward but not outward. It can't flatten completely, and it stops at around a 45-degree angle, but by changing the shape of those panel ends and making it a parallelogram, it can still form a gapless seal with the wall and the next panel. My wife thought the aesthetic of the angled panel would be better than that with the inset, so this design might be the all-around winner. But to be sure, let's look through the requirements checklist. Does it block the view looking down from the balcony? Yep, that's pretty easy. And of course it also blocks light by that same token. Does it reduce the sound from the main room and from the other bedrooms? Yes, because it has a full seal around the beginning and all the edges. When it's open, it won't block the upward view because it compacts against the wall. Being mounted on rails all the way through the opening motion should prevent it from falling down pretty securely. Because it's operated by a single mechanism pushing on that outer wheel, it could be automated. And since it's just one mechanism, it should be pretty reliable. Finally, both open and closed, it's pretty minimal and fits into the aesthetic of the building. So I think we might have a winner. However, until I build this, I can't know 100% that it's going to work. But the simulation shows that there is a physical opening mechanism that could meet these requirements. That's enough for me to move on to the next step of prototyping and experimentation. I hope you've had as much fun watching this video as I did making it, so I'll see you next time.